Okay, good evening everybody. We're going to be doing some questions today to help anybody doing A-level physics prepare for their exams. So do let me know in the chat if you have any particular questions, and I'll do what I can to kind of get to those as we go through the stream. I suppose the other thing is I do have masterclasses coming up. So if you are maybe doing OCR or AQA exams in particular on Friday when you've got your paper 1 exams, then I'm going to be doing some extra masterclasses based on the ones that I did recently that lots of people couldn't quite book onto because they kind of ran out of time or there weren't enough spaces left. So hello to everybody here, that monkey guy, Farah, Tanwar, Eri, hi. Now, these questions, good question, says somebody, is this directed towards all exam boards? The questions I'm going to do today are going to be useful for anybody doing A-level physics, but these particular ones are going to be based on the OCR predicted papers in like speech marks from PMT. So that means I can show it on YouTube. If you look at it, this is basically something that a lot of you might have already seen. However, a lot of the questions inside it can be applicable to students preparing for Edexcel, for AQA, for EduCAS, for OCRB, for CIE, for the International AQA, for IB Physics, basically anybody who's got physics exams coming up. Okay, so Isaac says, do I think AQA are going to make it easier this year? Yeah, I reckon AQA has some tough papers in 2024, 2023, and I suspect because they've made them too difficult and the questions weren't easy to understand what they were asking, I reckon AQA is going to be easier this year. Yeah, this one here is going to be like the other one that I did. So some of you might have seen I did a live stream on Friday where I went through the AQA predicted paper from PMT. This is just going to be using the PMT questions, and I'm basically going to go through these over the stream and then use that to kind of talk about different bits of physics and hopefully, yeah. Right, somebody says they're going to do this later in the week. Will it be uploaded on my channel? Yes, basically after this live stream, everything stays live as it should be, so that, well, not live, but it's kind of there on the channel so you can easily find it. I'll put it in on my main page on YouTube. You can find it under my exam playlist for this year. Yeah, actually, somebody says, your physics teacher said that the AQA paper is likely to be more accessible because schools threaten to switch exam boards. Yeah, basically, all of the exam boards are in competition. You've got AQA versus OCR versus Edexcel. AQA dominate GCSE. Edexcel have got lots of other things and they're like a big worldwide company, but they're all basically in competition for schools to use them rather than one of the other exam boards. And that means if AQA aren't making papers easy and accessible, teachers will switch. AQA make less money, so they can't really cover their overheads as nicely. And so all the exam boards basically want your custom. They want your teachers to choose their exam board, and therefore they're going to hopefully make all of the exams as accessible and fair as possible. Okay, right, so this one here is going to be the PMT Modelling Physics Paper 1. It says 2 hours and 15 minutes, so I guess what we're starting just after 8 o'clock. Hopefully we'll be finished by 10, if not by 11. Yeah, but basically this thing here, this is not, in my opinion, a predicted paper, but it is a good source of additional questions. Now, if you want to find more questions, all you need to do is head over to A-Level Physics Online. Hopefully you've been to this website at some point. And then if you go to more and you go to past papers, or you just find the past papers within my website, basically what you can do is find any of your past papers easily, and all you need to do is just select the exam board, select the level, select the paper, and then you can find lots and lots of things there. And also, if you were to tick these things over here, you can find the exam papers I've actually done where I've got work solutions. So if you are doing OCR and you want to find work solutions to 2022 and 2023 for modelling physics, you can find the video walkthrough on my website where I go through stage by stage. It's coming up any second. Any second it's going to be coming up. Come on, keep going, keep going, keep going. Let's do a quick refresh of that. Basically, this comes up any second. Okay, that's probably not the best demo of that, but basically on my website you can find the past papers that you need. So basically I've got work solutions for 2022, for 2023, for AQA, OCR and EdXL, and obviously as years go on I'm going to be adding more and more to them. I don't quite know why that didn't work. Right, let's have a look at some questions. Also, finally, the other thing is if you do want to do a last minute masterclass and some revision, I do have these and they're going to be on Wednesday evening and Thursday evening. So I'm going to be doing another OCR revision masterclass on Wednesday between 5 and 7. And then I'm going to be doing a AQA, A-level physics, paper 1 revision session on Thursday between 6 and 8. And I'll be going through everything you need for the paper. And this is basically rerunning the sessions I've already run. Those masterclasses are awesome. Thank you, Rufus, in the chat. Yeah, I reckon definitely worth having a look at. Okay, is this useful for AQA paper 1 revision? Yes, a lot of it is. So a lot of this stuff I'm going to be going through tonight is just basic physics. So you can keep me on in the background. And what I'm going to do is go through my approach to this paper. So the first one, we've got these things here. Which are these in order of decreasing magnitude? So we've got micro, nano, femto and pico. So a micro is going to be times 10 to the minus 6. A nano is going to be times 10 to the minus 9. So they're the ones that come up all of the time. We then have femto and pico. And this is something that you might not be so familiar with. Now a pico is times 10 to the minus 12, and a femto, often used in the kind of scale of atoms and things, is times 10 to the minus 15. So my approach for this question would be just to have a look at what we've got here, write them down, and then think, okay, we've got, sorry, that's micro, isn't it? Not milli. Micro, nano, pico, femto. So micro, nano, pico, femto. So here the answer would be C. Okay. Which row contains only vector quantities? So if it's only got vectors, it must have no scalars. So I'm just going to have a quick look through this and work out which of these are scalar quantities. Mass is a scalar, temperature is a scalar, energy, anything to do with energy is a scalar. So that means looking at this, the only one where we have vectors are momentum, force and displacement, all vector quantities, and therefore the answer is D. Okay. Somebody was asking about my work solutions on the website. When am I going to be doing the 2024 papers? I can't do the 2024 papers until they've actually been released by the exam board. So basically, I can't do any video walkthroughs for 2024. There we go. I can't do any 2024 workthroughs of these kind of videos until they've released them, which won't be until after your exams this year, I'm afraid. But of course, if you want to look at my solutions for 2022 and 2023, you can click on the video, you can select the question, and then there's basically me going through that in lots and lots of detail in slow time. Also, check that out. There's actually a piece of Lego where I made my own Lego glider and air track. So maybe massively over the top. Anyway, let's keep going with these questions. Okay, so Rufus says, yeah, the website design is killer. It's absolutely fire. I'd agree with that. Okay, a student wants to accurately determine the diameter of a wire. Which is the most accurate? So if there's a choice between a vernier caliper and a micrometer often has a gauge, a kind of clutch at one side. So as you close the jaws over a small distance, it doesn't apply too much force. So a micrometer is better than a caliper. This one says to measure the diameter at least 3 times and find an average. This one says use a micrometer and measure the diameter at least 3 times along different points on the wire and find an average. Well, I guess there's more words, so it's probably going to be better. So here, D is the better answer, so the answer for this is D. So the micrometer, it's often got basically jaws that look something a bit like this. Okay, and then there's this kind of sort of screw gauge inside, and it looks maybe a bit like this. Okay, and often you might find like a sort of knurled end, and basically what you do is you rotate that round, as you're clamping the jaws over the wire that you're trying to measure the diameter of. So a micrometer is the best method, and you want to do it at least 3 times along different parts of that wire. Okay, so the next question, the following velocity time graph describes the motion of a vehicle. Determine the displacement of the vehicle from its starting point. So I think what they mean here is after the vehicle comes to a halt, what is the displacement of that vehicle? Well, if you've got a velocity time graph, then the area underneath that graph is going to be equal to the displacement. So my approach to this would be looking at basically if we times the height of this, which is 50, and I've always just checked that every time you have a graph, just maybe highlight or kind of just underline what the units represent. And what we then need to do is just work out the area, and that's meters per second and time in seconds. And so we just need to work out the area. So that length goes from 5 to 15, so that's going to be 10. This length goes from 0 to 25, so that's 25. And basically we're going to add this side to this side and find half that value. And we're going to multiply that by the height. So it's kind of like a sort of trapezium rule thing. So let's work this out. If you've got the answer, put it down. We've got, okay, Joseph says A. Let's see if you are correct. So you've got 10 plus 25 divided by 2 times 50 is equal to 875. And therefore this displacement here is 875 meters. So the answer is A. Okay. Yeah, trapezium rule, excellent stuff, says John Doe. Basically, if you want to find this paper, all you need to do, actually, shall I show you? So if you want to find this paper, what you need to do is you basically need to go to PMT, you go to Physics and Maths Tutor, and they've very kindly allowed me to use the video tonight, so, oh, why is it doing that? Okay, basically the front page in the middle at the top, it says predicted papers. What you can do is you can go there, you can select what you're going to be doing. So let's look at physics predicted papers. You can then access the bundle, select the exam thing, and then you basically get the papers that you want. And basically all you need to do is go there, and it's obviously a great marketing thing for them because that allows them to get your information about who you are, what your email address is, so they can market all of their other services they do. But the people that kind of wrote this and stuff, and also PMT, I asked PMT if I could use this, and they said yes, because I guess it's helping them, it's kind of showing what they're doing, and also allows me to have a good source of questions. And this is going to be for OCR. Okay, an object of mass 2 kilograms is moving vertically downwards through water. We've got upthrust and drag acting on it. Now, even though this is a multiple choice question, I'm going to start with a diagram. So we've got an upthrust, which is 13, and then we've also got a drag force, which is equal to 9.0 newtons. Okay, so basically they're going to be the forces acting upwards, and if we've got a force acting down, it's due to its weight, and so if the mass is 2 kilograms, I'm going to multiply that by I'm going to multiply 2 by 9.81, and this means that the arrow down is going to be equal to about 19.6 newtons. Now, of course, we've got 13 up and 9 up, so that's 22 newtons up and 19.6 newtons down. So the resultant force on this is going to be up, and it's going to be about 2.4 newtons, even though the object happens to be moving down at that point. And therefore, the object, which statement about this object is correct at this time? I would say that if it's moving downwards, but there's a resultant force upwards, I would say it's decelerating. So this, I reckon the answer is B. Okay, is that what they say? Okay, no, actually. Right, so I do have the mark scheme here. I'd say B for that because there's a resultant force up, but it's moving down, so it's decelerating. PMT say for number 5, the answer is B. Yeah, good, so it's decelerating. So here, the answer is B. But I think actually, yeah, so the answer must be B, so that's all good. So we've got something. Maybe, for example, it's a large rock that's been dropped into water, and what it's happened is it's gone under the surface and it's still moving quite quickly, and now it's slowing down, it's decelerating, as we have maybe quite a large drag force because of its velocity. Right, okay. So I'm just going to look at what people are saying in the chat. Is this for AQA, EdXL? No, this is an OCR question, but I think by now you must realise that A-level physics is just A-level physics, and a lot of these questions could apply to any exam board. Okay. Yeah. Okay. By the way, if anybody puts random stuff in the chat, all I'll do is I'll basically get you to basically just be banned completely. So if you put random stuff in the chat, what I'll do is I'll just ban you from the kind of chat for the future. Is this a predicted paper, or is it a remake of some OCR multiple choice questions? I think that basically you can't predict what's going to come up in the exam. Prepare for everything and you're going to be absolutely fine. If you try and predict what's going to come up based on what came up this year or last year or the year before, then it means you're going to not focus on the right things and you're just going to focus on a narrow part of the course. So this is not a prediction. These are just similar style questions to what come up every year. Okay, we've got the objects undergoing a completely inelastic collision. What's the final velocity of each object? So if it's completely inelastic, then afterwards the two objects are going to stick together. They're going to move at a combined velocity v, and their combined mass is going to be equal to 50 kilograms. So we can basically say that before the collision, we've got the mass of this, which I'm going to call m1, going at u1, plus this mass, m2, u2, is going to be equal to the total mass, m1 plus m2, times v. Okay, so if we've got conservation of momentum, we've got that momentum added to that momentum is equal to this final momentum. So if you've got 2 times 30, that's 60. We've got 5 times 20, which is 100, and that's going to be equal to 50 times v. So you've got basically 160 over 50 is equal to our final velocity. So 160 divided by 50 is equal to 3.2. And so I would say after the collision, because it's completely inelastic, the two things stick together, and that means they both travel at 3.20 meters per second. So the answer for this would be C. Okay. Now, if it was elastic, you'd have a different kind of thing, because we'd also then have to consider the fact that we've got, if it's perfectly elastic, we're going to have conservation of kinetic energy. However, here we don't. So there's going to be more kinetic energy before the collision than afterwards. How do you know they stick together? They stick together because it says it's completely inelastic. So imagine things which aren't elastic at all, kind of very much a plastic kind of material. The two things just stick and then they move off together. Okay. Right, if the distance between the Earth and the Moon is 384,000 kilometres, determine the gravitational force of attraction of the Earth on the Moon. So we've got the Earth and we've got the Moon. And I think this wasn't a good question, because normally if we talk about the distance between things, we talk about the distance between the centres of mass. Okay, now the size of that gravitational force is going to be equal to minus gmm over r. Now I don't have a data sheet, so let me just grab one. Okay, so I've just got like a small OCR data sheet, and this one here says basically F equals minus gmm over r squared. So the size of that force is going to be equal. Well, I guess we just want to look at the gravitational force. We don't really care about the negative symbol. G is going to be our gravitational constant, which is given to us as 6.67 times 10 to the minus 11. Yeah, so I kind of wrote it down from memory, checked it in here. We've got the mass of the Earth. Well, let's say the mass of the Moon is little m. So that's little m and that's big M. So that's going to be 7.35 times 10 to the 22 multiplied by the mass of the Earth, so 5.97 times 10 to the 24. And we're going to divide that by the distance between them. Now, I think that this one here wasn't a good question because it says the distance between the Earth and the Moon is this much. Now, I would say normally if you give a distance to something, it's the distance from a centre of mass to another centre of mass. And also, yeah, you're given that equation for AQA as well, but they call it, I think, GM1 M2 over R squared. I guess they've got the Earth's radius, so you've got this Earth's radius, you've got that distance from the surface of the Earth to the surface of the Moon, and then you've got this distance here. So I would say that there wouldn't be a real exam question where it's this ambiguous. So somebody says, am I going to be going over the AQA paper on Thursday evening? No, I did the AQA paper last week. So if you want to catch up with the PMT AQA paper, you can find that on my live streams. You can find it on my main channel page if you look at the lives, and you can basically look at the whole thing there. So really, I guess the distance we're going to go for, if we add the radius of the Earth, so that's 6.37 times 10 to the 6. We're going to add that to the distance between them. So 384,000 times 10 to the 3, because that's in kilometres. And then we're going to add that to the Moon's radius, so 1.74 times 10 to the 6. So the size of that force, and bear in mind, you can see what I'm doing here, is I'm still drawing a diagram, I'm still writing out my equation, I'm putting in my numbers, and then solving this. So let's have a look at what this is. So 1.74 times 10 to the 6 plus it's R squared, isn't it? Okay, right. Apologies about this. Yes, so basically it is R squared says 3E. I should have done that. This is the kind of style of question that could potentially come up on an AQA paper too. But this is very much an OCR paper 1 question. So right, let me do that again. Actually, no, let me look up at my answers. Okay, so I'm going to square that. And then I'm going to do right, basically, I've kind of messed up the answer on my calculator. If I was doing this in a real exam, I would definitely be doing it properly. However, the pressure of a live stream and knowing that there's people watching me meant I've kind of messed up what I put on my calculator. So I would say for something like this, do you know, I'm going to work it out again. So I just don't like this question. I think it's badly worded. Right, 1.90 times 10 to the 20. So I've done that, and the answer is this one over here. So the answer would be C. Well done for everybody that. Yeah, I was cooked a bit there. Okay, this question here, probably you've got to realise that in a real exam, they would actually give you these numbers in a numerical order. So the first answer would be the lowest number, and the last answer would be the highest. So that's something also to note is that when you're doing multiple choice questions, they always give you the answers in numerical order from smallest to largest. Okay, which statement below correctly describes the oscillations of a child on a swing that is driven only by the push of an adult? So you may assume that the child's swing system behaves as a simple pendulum. So if you've got So we're going to assume that we've got a small angle of theta, and the pendulum is going to be going back and forwards. Because it's moving, there's going to be, in real life, some air resistance, so the system is lightly damped. The natural frequency of the child swing system is proportional to the length of the swing. Well, the frequency is going to be related to 1 over the time period. Okay, so the natural frequency is related to 1 over the time period, but the time period is equal to 2 pi root L over G. Now then, OCR people, learn that equation, take a picture of it, take a screenshot. AQA people, you know that, it's given to you and it's just something that you're used to using all the time. OCR people, you're not often given that. But basically what this means is that the time period is proportional to the square root of the length of that. So I would say that this is not an OCR, but you should know it. My advice would be, if you are doing OCR physics, just be familiar with the equation for a pendulum and also the equation for a spring mass system. This is something you should have done practical work on when you've been looking at oscillations. So I feel, even though it's not explicitly stated in the OCR specification, you should still know that that's something that you should be familiar with. So here, T is proportional to root L, so it's not 2. Now, the next one, we don't even need to do, because it says here, only 1 and 2. Well, it can't be that one. Only 1 and 3, possibly, but it can't be only 2 and 3, and it can't be 1, 2 and 3, because we know that 2 is incorrect, so B must be the correct answer. Let's just confirm that. When the adult pushes should match the period of the swing to achieve maximum amplitude of oscillations. When the adult pushes, this should match the period of the swing in order to achieve the maximum period of oscillations. Yeah, so basically, if you've got the driving frequency equal to the natural frequency, we get resonance. So despite that sentence not being that clear, this is actually a true statement. Okay, yeah. Right. Okay, right. Which of the following is not an assumption for the model of kinetic? Which of the following is not an assumption in the model of kinetic theory of gases as applied to a container filled with that gas? So there are certain things you might remember raved if you've been looking at like my daily workout books and so on. So which of these is true? So let me know which you think in the answers here. Number 9, what do you reckon the answer is? James Evans, straight in with the D. Excellent. So you've got a D straight away. Other people, Farah says D. D is not true, says Chidambaran. Hello again. We've got AG2 San D. Danny says D. George D. Yusra D. Izzy D. D is the Ron. So the collisions between the molecules and the walls are inelastic. That is not true. In actual fact, they are perfectly elastic collisions. So there's going to be no kinetic energy lost as the particles hit the wall and then bounce back again. So this is not an assumption, D, because that is an untrue statement. We have a large number of molecules. We've got negligible forces between the molecules and they occupy negligible volume. So we're going to have negligible stuff all the way through this, and therefore the incorrect one is D. Okay, I think we're doing all right, aren't we? Okay, and then number 10, what have we got? So, the following volume temperature graph was obtained in an experiment where the pressure and the mass of a gas was kept constant. The student extends the line to meet the y-axis and obtain the value for the y-intercept, and then they blah, 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 blah. So, what would be the experimental value of absolute zero? So this is something where in the lab, you might look at something where you look at the volume and the temperature. So the volume increases with temperature. Gets hotter, gets bigger, straightforward. But if you were to extrapolate the line and you kept on going until the value on the y-axis was equal to 0, this would be the most negative temperature possible, and that's going to be okay. That's going to be our 0 Kelvin point. So use this data to determine the experimental value of that. Okay, so let's see. So we've got, I'm just going to write down y is equal to mx plus c. It says the y-intercept is 10.5. and that's equal to the gradient 0.035 times, oh no, sorry. If you had something where the value on the y-axis was 0, we would say that 0 is equal to the gradient, which is going to be 0.035 times x, and we want to work out what that value of x is, plus our value of the y-intercept, which is 10.5. So that means x is going to be equal to minus 10.5 divided by 0.035. So I've just used the y equals mx plus c equation, the most important equation in A-level physics. And this gives me an answer equal to minus 300. So I haven't even looked at what the numbers are yet, but now I've got my value, which we know is going to be about minus 273. The number is this one over here, and therefore the answer is C. C. Yeah. Right. You can get the past paper. This one happens to come from PMT. I'll put a link up to it after the stream in the description. Okay, answer is C, says Zainad. Yes, it is. Right. Which of the following provides evidence that electron energy levels are discrete? Well, the photoelectric effect provides evidence of the wave-like properties of light, so it's not that one. Electron diffraction provides evidence of the wave-like properties of electrons, it's not that one. Beta minus decay, I guess that's just something. But the line spectra, the fact that we only get certain frequencies of light being emitted or maybe absorbed, is because we only have certain discrete jumps of electrons giving out photons from one level to another. And therefore, because we've got these discrete energy levels, there must be photons at certain frequencies. And therefore the answer, as everybody's saying in the chat, well done everybody, is C. Okay. All right. Number 12. Anytime you get a question with SHM, there are lots and lots of equations that you could potentially use. Of course, you can use your highlighter. So we've got the mass of the object. It's undergoing simple harmonic motion. Its amplitude is 50. We've got a frequency. What is the maximum value of its kinetic energy? So don't look at the numbers. That's not a good thing to start with. Just think about some physics. So the kinetic energy is going to be equal to half mv squared. And of course, Vmax for something which is oscillating with simple harmonic motion is going to be equal to omega A. And omega is equal to 2 pi over t. So from memory, there are some things I've written down. I'd also probably, if I was in the exam, and actually Ollie RXT, Eiji-san, yeah, we've got some good stuff there. Dr. Lithium, I love your name. You find the max speed and then use a half mv squared. Perfect. Okay, so I'd write these down. I might just have a quick double check that I've not messed anything up. So EK, the kinetic energy, is going to be a half times the mass times V max squared, which is equal to omega A, which is going to be 2 pi A over T squared. And then I'd probably put the numbers in, so that's equal to 0.5 times 0.10 times 2 pi times 0.050 divided by, oh no, sorry, it's 2 pi over T, so that's going to be 2 pi F, isn't it? Which I suspect a lot of people are saying. So, sorry, I'll just write it down here. The kinetic energy is going to be a half times the mass times 2 pi Fa squared. So that's 0.5 times 0.10 times 2 pi times 0.60 times 0.050 squared. Okay, just bear with me. I think, looking at my desk, I think I've got like ink everywhere. I don't know where that's all come from. I guess leaning on a pen. Anyway, let's get back into this. So I've got 1.78 times 10 to the minus 3. And therefore the answer would be the first one, which is A. Well done, everybody. Okay, right. Okay, light of wavelength. I might need to get myself a bit of extra paper for this one, actually. Okay, right, so the next one says light of wavelength 600 nanometers. So lambda is 600 times 10 to the minus 9. We've got 300 lines per millimeter, but that's not D, is it? If we've got 300 lines per millimeter, then the distance is going to be equal to 1 over 300 times 10 to the 3. So don't forget that. Often they will quote you the lines per millimeter, but that's not going to be the distance between the diffraction gratings. So we've got that on the screen. So we know that d sine theta is equal to n lambda, and we want to know what the maximum value of n is going to be when theta is equal to 90 degrees. Okay, so effectively, imagine you've got a screen up here, and you're shining light through it. You've got the first or zeroth order, you've got the first, you've got the second, you've got the third, the fourth, the fifth. There's going to be a point where this angle here is equal to 90 degrees, and that's where suddenly these things aren't able to actually land on the screen. And so that's going to be the limiting factor, and therefore we could say that n max is going to be equal to d sine theta, but you've got sine of 90, which is 1, so that's just d, divided by lambda. So that's going to be equal to 1 over 300 times 10 to the 3 divided by 600 times 10 to the minus 9. I guess we get a lovely kind of number here, so that's going to be whatever that is. I'm just going to work that out. That's equal to 5.556, and therefore, because n has to be an integer and it must be less than this, n is going to be equal to 5, would be my answer. Okay, everything all right? Did the Wi-Fi go a bit weird just for a second? Yeah, so I would say the answer for this would be C, which is equal to 5. Okay, I think we're almost done with the multiple choice questions. So for this one, we've got a real black body radiation curve for a sun-like star as shown below. Determine the surface temperature of the star given that the Wien's constant is 2.9 times 10 to the minus 3 meter Kelvin. So the first thing we want to do is look at the graph, and I would say if you're going to be doing this in an exam, then oh, here we go. Hello, Z Physics. You're in the chat. I was wondering why people kept on saying Z Physics in the chat. So yeah, Z Physics. The Z Physics is here, just to kind of sort of see what's going on. Right. Also, by the way, if you do want masterclasses, I'm doing some this week, but so Z Physics. So he's got some on his website. If you go to his YouTube channel, you can find out what he's doing. I think he's doing EdXL, OCR, and AQA on different evenings this week. I'm going to be doing some others, but there's no clash between the two, so you can always go to both if you wanted to. Right, so I would say to find the maximum value, use your ruler and just draw it in with like a pencil line, so it's very clear how you got to the maximum value. And I would say this is somewhere around about 460 nanometers. And then of course you are given the equation, aren't you, for this? But the way that they give it to you is a bit weird in the way that OCR do things. So I think they give you something that says, I don't like the way that OCR do it. They say basically lambda max is proportional to 1 over t, and therefore lambda max t is going to be a constant, but the constant happens to be this number here, which is 2.9 times 10 to the minus 3. So the maximum surface temperature is going to be equal to this constant of 2.9 times 10 to the minus 3 divided by this number here, 460 times 10 to the minus 9. And then let me just work this out. People are saying B, which is good. Okay, right. People are saying name a more iconic duo than Z Physics and Physics Online. Yeah, he's pretty good at climbing as well. He was a lot better than I was at my arms, ate for days afterwards when we did some climbing the other week. So this has got 6,304. And again, with multiple choice, once you've worked out the answer, go and have a look at what that's closest to, and I reckon this is going to be B in the answers over there. Okay. Right. What is the correct order of evolution of a star whose core is 22 solar masses? So I guess if you've got something which is that big, it's well beyond the kind of sort of Chandrasekhar limit. And so, you know, if it's something like our sun, it might do something like this. Okay. However, this is much more massive, and therefore at the end of its life, after it becomes a super red giant or a red supergiant, it will basically implode, and whatever's left behind in that core is going to form a black hole. So I would say for this one, the answer is probably going to be A. Says Herman, says Jack, says AG2 San, Izzy, excellent work on the multiple choice things there. So lots of people getting the right answer for that. Okay, so many more people, sorry. We've got Izan Dali, we've got Chidambaran, we've got Sahith, so lots of people there. Right, for this one, actually, do you know what I'm going to do? I'm just going to have a quick break, and what I'm going to do is just clean up some of the ink before it spreads too much in this in the office. Okay, is everybody ready for later this week, or are you just wanting to get it over and done with? Because I guess for a lot of you, it's probably still like 3 or 4 days away, and for many people it's going to be their first exam. So sometimes just wanting to get somebody said they're excited for Friday. Ollie, excellent stuff. Okay, let's see if that works. I don't know if this is meant for humans, but we'll see. Oh, look at that. It seems to be working. Okay, right. Yeah, so I suspect a lot of people at this time, you've done most of your revision, you've probably done most of the papers. If anybody would like to sign up for my A-level masterclasses, you can do that on my website, which is A-level Physics Online. Basically, all you need to do is you just need to go to A-level Physics Online, and from the main front page, it says A-level masterclasses. I've got a new booking system that I've been putting together today to make things easier, and basically now you can see what's coming ahead. I've only put in the remaining paper 1 masterclasses because basically I had people emailing me at 2 o'clock in the morning on Sunday morning saying, oh, I've missed out signing up for the AQA class I was doing on Sunday. Am I going to be doing another one? So yeah, I thought I'd put some in this week here, and then as you sort of look through this booking calendar, what I'm going to start doing is adding other things as well. So I've just put in a 3A, but I'm going to be doing other paper 2 masterclasses for anybody who's not actually been on one so far. So there will be kind of plenty more stuff that I'll be doing over the coming weeks. Okay, right. There we go, a small ad, because basically this is my job now. I'm not a full-time teacher, although actually I am teaching a year 13 class. I'm actually teaching a year 13, I've got 2 different year 13 groups I'm teaching in Bath at the moment, and so I'm going to be there on Thursday with them in person in the classroom, kind of doing work with them, and I suspect when I go in on Friday when I'd have my other lesson, they're probably going to all be in their exams, so there's going to be nobody there. But basically I'm still a part-time teacher doing some year 13 stuff, and I'm actually teaching OCR-A physics at the moment. Okay, right, that class might be so lucky, I don't know. They just seem like normal people like the rest of you out here. Okay, let's do some questions. Describe how an experiment can be carried out to determine the equivalent spring constant of two springs connected in series by plotting a suitable graph. Now, a question like this, I'm not going to write the whole answer out, but I think it's worth adding to your answer maybe a diagram. So maybe you've got the two springs, so you've got that one and you've got that one, and then I guess you've got the mass underneath it, and of course they're going to be extended through a certain extension. So are we calling it X or E? Let's have a look. So yeah, basically we've got a certain extension of that spring. Now there might be things that you can add to the diagram. For example, you might have maybe a ruler, and in order to show that that ruler is actually going to be vertical, you might kind of add in a diagram showing something like your set square over here that can be used to make sure that that thing is vertical. Okay, so we're going to be measuring the extension as we add different masses. You might also include in your answer the graph that you're going to be drawing. So maybe what we're plotting is the size of that force acting down the weight, and we're looking at the extension, not the total length, but the extension, which is how much longer that spring has got. And I guess we'd be wanting to get this region here, where you have a straight line, and then of course you'd show that you would basically be able to look at some values on this gradient to work out the spring constant. Okay, so a question like this, I would say, anytime you get an experimental thing, try and write in bullet points in a clear, logical manner. Think about the measurements, and when you write down the measurements, also include the instrument. So for example, if you're going to measure the extension, say really clearly that you'd measure the extension using a ruler. Okay, how would you minimize uncertainties? And this might be something as simple in this case as making sure that your eye is level with the thing that you're actually measuring. So you're going to reduce parallax error. Maybe making sure that the ruler is vertical using a set square. That's how you're going to be minimizing uncertainties. Think about what you're going to be doing with the data. And in terms of data, we want to have repeats. And if you are taking repeated values, that allows you to get a mean because it allows you to spot any anomalies. And yeah, basically a lot of this stuff is really obvious things that people forget about all the time. Okay, of course, somebody else here says about, Chidambaran says about comparing to y equals mx plus c, determine the gradient, use that to calculate spring constant. Because we know that f is equal to kx, then basically here the gradient of that line is going to be equal to our change in weight divided by the change in extension, which is equal to the spring constant. So don't forget, say, how to actually measure the value that you're supposed to. So these are the kind of things that if you're going to be doing like a longer explanation, especially about practical things, if you have like a bit of a diagram, that can help. If you've got a graph or an equation, that can help. Write in bullet points, but sometimes just state the obvious things. What you're measuring and how you're measuring it, how you're reducing uncertainties, and also what you're doing with the data to actually plot the value they're wanting you to get. Okay, yeah. Right, we now have a question that when I read through it earlier, I didn't understand it because of the diagram. It looks like they've got a mass which is attached to both these things at the same time, so I'm not sure how good that is. Okay, right, somebody says, is it possible, this is a good question, is it possible to learn all of mechanics and further mechanics in 10 hours as it's your weakest topic? Basically, you don't need to learn it all in 10 hours because you've already got a good standard of knowledge. It might just not be as good as it could be. So it doesn't mean that you are starting completely from scratch. You just need to refine it over the next 10 hours, and you can do a lot over the next week. Okay, somebody else says that, yeah, there's lots of stuff here. Now, a lot of people are asking questions about how can you learn certain things. I would say you've all got a good basis because you've been doing physics for the last few years, week after week after week, and you're so much better than you were when you were little GCSE students. If there's anything you're not particularly sure about, and you haven't already done so, have a look at my A-level website, which is A-level Physics Online, and I've got videos there where I explain everything to you. So if, for example, you're not sure about Young's double slit experiment, or you're not so happy about electricity, I do have videos there that you can watch where I explain lots and lots of these bits of physics. Okay. Yeah. Okay, so this question then, we've got some wires, we've got this mass, given that the wires have the same cross-sectional area, show that ES over EB equals FS over FB. So I'm going to start by saying that the Young modulus is equal to the stress divided by the strain, and the stress is equal to force over area, and the strain is equal to the extension divided by the original length. Okay, so if we take this, we can then say that the Young modulus is equal to the force times the length over the extension times the area, and therefore the Young modulus divided by the force is equal to the length over the extension times the area. Now, in this case, we get two wires that start with the same original length. They extend by the same amount, so x is going to be the same, and also they have the same cross-sectional area, so these three things are the same, and therefore the ratio of the Young modulus to the force should be constant. So if we think about the Young modulus of the brass divided by the force in the brass, that's going to be the same as the Young modulus in the steel divided by the force in the steel, and then all we need to do is basically put this down here and that one up there, and then we find that EB, or I guess we could do it the other way around, we could basically then say that ES divided by, actually I'm not going to do that red line, if we think about swapping these two values around, we can then say that ES divided by EB is equal to FS divided by FB, which I guess is what they've got up here. So that would be my approach to that question, looking at that formula for Young modulus. And this is A-level. Okay. Everybody happy? Cool. Right, so the next one. Show that the magnitude of the force in the steel wire is about 10 newtons. We've got the Young modulus of brass and the Young modulus of steel. So they happily have given us these things where the numbers are they go into each other quite well. So the Young modulus of brass is 1 times 10 to the 11, and the Young modulus of steel is this. So I'm just going to write down that equation again. ES over EB is equal to FS over FB. So ES is 2 times 10 to the 11. ES is 1 times 10 to the 11, and that's going to be equal to FS over FB. Okay, so that means 2 times FB is equal to FS. Okay, so we can look at the ratio of the forces. So basically, whatever the force in the steel is, we're going to have twice that force in the brass. Okay, and that means the other thing that we know here is that basically if we think about a force diagram, there's going to be the force acting down due to the mass, and it's a mass of 1.5 kilograms. So I'm going to say that's equal to 1.5 times 10 to the 9 times 9.81 newtons. So that's going to be the weight force down, and that's going to be equal to the force due to the steel wire and the force due to the brass wire. So basically this force added to that force is this, which is going to be approximately 15 newtons, and therefore we can say that 15 newtons is equal to Fs plus Fb, but Fb is going to be, so Fs is going to be 2Fb, so that's going to be equal to Fs plus Fb, but Fb is going to be Fs over 2. Does that make sense? So basically we can say that Fs is equal to Fb over 2. And here, that 15 newtons would be equal to Fs plus Fb. So that's that. And that means 15 is equal to 3 over 2 Fs. So that'd be 230 divided by 3, so Fs is equal to 10 newtons. Okay, now that would be not enough, I don't think, to get the right answer. You'd actually have had to calculate it, so I guess we'd really have had to say 1.5 times 9.81 by 2 divided by 3 is equal to Fs. And if you just did that, I don't think that would get you the marks in an exam, because for a show question, it says up here, show, it's about 10. We'd have to say that basically Fs is equal to 9.81, which is approximately equal to 10 newtons. And I think that's what you'd have to do to get the mark, because in a show me question, you always have to give your number, or you're working out to one more significant figure, so you'd have to quote something like that. Okay, that would be my opinion. Okay, all good. Okay, Cosmic has asked a really good question. Is it impossible to get 100% even if you know the specification inside out? I don't know, I reckon I could get 100%. Maybe not in the time, but I reckon it is possible to get to 100%, or pretty much as close to it as makes any difference, really. So yeah, but I would say that, I don't know, I think I wouldn't get 100% because I'd probably lose marks here and there on the longer 6 markers and the explanation questions, especially seeing stuff the first time under exam conditions. I'd find it difficult. But yeah, I don't know if anybody actually got 100% last year. Maybe I need to ask the exam boards what the range of marks were, because it'd be amazing if somebody actually did. I think I've definitely got 100%. When I was at school, I got 100% in lots of mechanics things in maths. But in maths, it was a bit easier because it's just numbers, and you definitely got the right answer, and you knew that you got the right answer. So I think because there's less writing in maths, it was easier to get 100% there. Yeah, right. The next question says, if the extension produced in each wire is 5.36 times 10 to the minus 5, determine the cross-sectional area of each wire. So for this one, how would I be doing it? I'd probably just be using this equation that we said before, that E is equal to FL over XA. I guess if we think about steel, Fs, we know that the Young modulus is given to us as 2.0 times 10 to the 11. The force was given to us, because we worked it out previously, as 9.81. The length was given to us as 1.5. The extension is up here, so that's 5.36 times 10 to the minus 5, and that's going to be multiplied by the area. So basically, throughout this whole question, we've been given lots of information for the Young modulus, for the force, for the length, the extension, and therefore we can use that to work out the area, which I think when you do it, I may as well probably work it out, I guess. So that's going to be 5.36 So I've got 1.37 times 10 to the minus 6, so 1.4 times 10 to the minus 6 square metres. And I'd be given my answer to 2 significant figures, because we were given the initial length of the wire to 2 significant figures as well. Okay, hopefully that's all right. Yeah. Right, tea break sorted. I feel like there's just a an unlimited amount of questions. Does everybody want me to keep doing more? What tea am I drinking? I'm drinking cheap tea that's in the office, so it's like a non-brand tea bag. I couldn't find any of my proper physics online mugs. They're all in the wash in like various kind of dishwashers around the building. So yeah, it's just like an average tea, quite milky and actually quite cold now, so not the best. Yeah, more? Milk tea is so bad. No, milk tea, absolutely the best, absolutely the best. Right, a golfer hits a stationary ball, blah, blah, blah. Calculate the change in momentum of the golf ball. So the change in momentum is going to be equal to its final momentum minus its initial. Now we've got a mass of 0.045 kilograms. The final velocity is 40. And then the initial velocity, because it was initially stationary, is 0. So it's just going to be that, which equals 1.8 kilogram meters per second. Okay, there we go. It then says the contact time between the golf ball and the club. The contact time between the golf club and the ball was 9.2 milliseconds. So often when you've got collisions, we have very, very small times. The average force on the golf ball. So we know from Newton's second law that the force is proportional to the rate of change of momentum. And therefore the change in momentum is going to be equal to the force times the... Oh yeah, but that's basically all we need, isn't it? So the change in momentum was what we worked out up here, so that's 1.8. The collision time was 9.2 times 10 to the minus 3, which is 195.6. So I'm going to say that's 2.0 times 10 to the 2 newtons. And that's giving my answer to two significant figures like the data up here. Okay. Yeah. Z Physics says you will definitely bring a protractor. Yeah, I reckon. Yeah, just a small Helix one. I think they cost about 20p or £1 maybe. They're definitely less than a drink that you get in the supermarket. Definitely less than a can of Monster, but far better for you than a can of Monster. So yeah, make sure you do have your protractors just in case you need them if you're doing any scale drawings or something like that. Right, in the space below, sketch the path of the ball, calculate the initial velocity, the initial vertical component of the ball. So if we're doing a sketch, I'm going to draw the ground with a ruler. So that's that. It says that the initial, what was it, the 30 degrees above the horizontal. So if it starts here, I'm just going to mark out my line. So this is going to be, because we're sketching something, you may as well do it as accurately as possible. I'm just going to draw this thing here to be my 30 degree to the horizontal. And then we're going to have basically something that goes up in the air and then comes down like that. Look at that beautiful curve. There we go. I guess we can also say that if it was travelling at 40 meters per second at an angle of 30 degrees, we want to calculate the vertical component of velocity of the ball, which is going to be uy. And uy is going to be equal to 40. I guess this is like the closed side, so it's going to be sine. So it's going to be 40 sine 30, which of course the mathematicians amongst you mean that sine 30 is just 0.5, so that's equal to 20. So it's going to be 20 meters per second. I guess one criticism I do have is they keep giving GCSE units, so that would be meters per second in my opinion. Okay. Somebody says, so Jackaran says, is it too late if you don't know some topics at this time? No, it's not. You can still learn a lot over the next 24, 48, 72, is it 96 hours maybe? Maybe a bit less than that, maybe 72, 78. There's like basically 80 or 90 hours or something like that until your exam on Friday. And you've got lots of time, because it's not like you have to learn everything from scratch. You just need to boost the knowledge and the stuff that you already know. So there's plenty of time still to learn lots of things and really improve. Can invigilators give you rough sheets to draw diagrams so you have space to write out methods of answers? I think that they tend to want you to not use extra diagrams because that work can't be marked. I think that it's better to use the extra pages at the end of the exam if you've got extra work that you need to be doing. Often though, there's often space within the exam paper to do stuff, but I do feel that ideally you'd probably want to use the extra sheets at the back of your exam paper first. It's easier to reference that, but of course if you did run out of space, I'm sure the exam invigilators would give you the paper. Yeah, I'm pretty sure they can. Right. Okay. Show that the total time of flight of the golf ball is about 4 seconds. So in my masterclass, we've kind of looked at different sorts of projectile motion, and I'm just going to think about the first half of this motion until it gets to this point. So that's basically the first part of the journey, and then 2 is the second part. Now for the first part of the journey, I'm going to write down suvat vertically down the page, and I'm going to say that upwards is my positive direction. Now we know upwards, its initial vertical velocity uy is what we worked out here, so that's 20 meters per second. At the top, the velocity goes to 0, and we know the acceleration is going to be minus 9.81. So although it's moving up, it's decelerating down, and we want to find t, so we can say that v is equal to u plus at, so that's the only suvat equation without s in it, and therefore t is equal to v minus u over a, which is equal to 0 minus 20 divided by minus 9.81, and that's equal to 2.04 seconds. But of course that's going to be the time for the ball to go up, and that'd be the same time for the ball to come down. So the total time is going to be twice this, which is 4.08, which is approximately 4 seconds, which is what we wanted to show in that question. Okay, now I've never actually done that question before, but it is so similar to hundreds of other CVAT questions I've done over my life, and basically the more past papers you do, the better you get at these methods until you start to realise that similar things come up again and again and again. Okay, right. When the ball lands on the ground, it continues to roll for another 2 seconds before it comes to rest. Show on the graph how the vertical component of velocity changes over the entire 6 periods of travel. So, right, what do we know? I guess we knew that it took 4 seconds to go from the start to the end. So I'm just going to put like a construction line here at 4 seconds. Okay. The other thing is that it started going up at 20. When it got to the highest point, it was at 0. And then I guess it would be coming down. So when it hits the ground, it'd be minus 20. And so the first part of the graph, I'd be drawing like this. Okay, so I'm going to do that in pencil. Hopefully all of you can see that. And this is the velocity time graph for an object moving under a gravitational field. And of course, I guess actually in the vertical direction, the gradient would be 20 divided by 2, which would be 10. So here the gradient is equal to minus 9.81 meters per second per second. So the gradient is due to acceleration due to gravity. Okay, and then after 4 seconds, it's moving on the flat. So in the vertical direction, I'm just going to do it in red just to kind of emphasize that line. We'd then have something like this. So basically we'd have something like this where we imagine that that line kind of goes like this. That's supposed to be going up. So there's a negative acceleration until it hits the ground, and then it continues at 0 vertical velocity because it's moving along the flat. Yeah, if you were going to draw the gradient, if I wanted to actually work out the gradient, you would draw the biggest triangle you possibly can. They say the triangle should be more than half the length of the line, but you know, go big just go for the full line. So here, if you wanted to work out that gradient, it would be 4 minus 0, and here you'd have minus 20 minus 20. So the gradient would be equal to dy by dx, which would be minus 40 over 4, which is about 10 meters per second squared. Okay, right. Okay, in reality, air resistance affects the path of the ball while it's in the air. Describe how your diagram would change when air resistance is taken into account. So imagine this is what it looked like initially with no air resistance. I guess when you had air resistance, it wouldn't accelerate as high, and that means it would also start to decelerate this way, and I guess you'd basically get something like this. So it wouldn't get as high, and it wouldn't get as far. But for this question, you only need to describe, you don't need to explain why that is. Okay, so I think here, yeah, the ball reaches a lower maximum height, has a shorter range, it will hit the ground at an earlier time. So that's what the kind of model solution says. Basically, this is when you've got air resistance, so it won't go as high and it won't go as far, and it'll spend less time in the air. Okay. Right, by the way, people watching tonight, it'd be amazing to find out which exam board you're doing. So it'd be amazing to find out in the chat if everybody watching, by the way, you need to subscribe to put stuff in the chat. So hello to everybody who's there at the moment. You are all my amazing subscribers. Also, it'd be nice if I could get another 3,000 people to subscribe over the next month or so, because I'm almost at that 200,000 mark and it's like not quite getting there. So yeah, we've got AQA, AQA, OCR, OCRA, OCRA. OCRA, are people not subbed? Oh, in that case, I might have to turn off comments for people who aren't subbed in that case. OCRA, AQA, OCRA, AQA, AQA. Does 200k get you a play button, says Salvi Myers? No, it doesn't. I think I've got to get to 1 million. So I'm well behind free science lessons on my way to the 1 million plaque. But, you know, maybe at this rate, maybe in 100 years' time, maybe. Okay, OCRA, OCRA, OCRA. It's basically, oh, we've got an EdXL. So that Kira is EdXL. Yeah, so CIE says Sedem. Yep. RCAA. I haven't heard of that one. OCRD. Okay, I don't think you know what you're doing, do you? Educas says Divs. Yep. Yo, Busy Redstone, OCRB. Rohan, AQA. Yeah. Right. Somebody's saying, John Doe says, free science lessons, Z Physics, Physics Online. I'm up for it. Yeah, I'm very happy to meet other YouTubers. Some of you might have seen the video I did recently with not just Z Physics, where we did some physics stuff, and I've got some more stuff coming up on his channel. Also, I did some with Miss Estrick, who does biology stuff. We did some lovely stuff together, so that was amazing. But yeah, free science lessons, doesn't do as much physics. He's done some GCSE stuff, but not the A level. Okay, I feel, should I do the rest of this tomorrow, or should I do it all today? Would you rather I just smashed through the whole paper, or just came back and did it again tomorrow? Let me know. Right, let's do it. Okay. Release of predicted papers for AQA A-level physics. These are not predicted papers, people. These are just, the word predicted gets you lot to watch it tonight. But yeah, basically power through. People will say all today, look burned out. Yeah, do you know, I'm quite tired. I've been doing a lot of live streams Friday, Saturday, Sunday, last Thursday, last Wednesday. I think, did I do anything on Tuesday? Basically, I've been doing so much stuff, but right, let's just do it, okay? Right, let's just keep going with the whole thing of physics. If I start to look really tired, what I'll do, I'll just turn off my face so you can't see my tired eyes. But anyway, I'm good at the moment. Define the specific latent heat of vaporization of a liquid. So if it's latent heat, then it's, well, specific just means it's per unit mass. In this case, it's going to be per kilogram. If it's vaporization, it's going from a liquid to a vapor, or liquid to a gas, and therefore the amount of energy to change the state of 1 kilogram of a liquid into a gas at a constant temperature. So that's something that could be asked potentially. They tend to not ask as many definitions now as maybe in previous years. Okay, explain why the specific latent heat of fusion of water is much lower than the specific latent heat of vaporization of water. So if you've got the latent heat of fusion, that's often much, much smaller than the latent heat of vaporization. The difference being that in this, you're basically taking some water molecules, in fusion, you've got things which are in a solid, and you're basically making that stuff into a liquid where the particles aren't really separated that much. We're just kind of breaking up the bonds between them. Whereas when you were going from a liquid to a gas, we've actually got to completely separate the particles away from each other, and that's why a lot more energy is needed to not only break the bonds but then actually separate the different molecules. Okay, so somebody says Chidambram again saying large change of potential energy for vaporization as all the intermolecular forces break, low change in intermolecular forces from solid to a liquid. Perfect. Okay, right. Somebody says, can I give out free flashcards beyond particles? I'm afraid a lot of people are loving my flashcards. Well, I'm not afraid about that, but I've made some flashcards for AQA. You can find them in my online shop. They're only £2.50, well worth buying, but I haven't made them for the rest of the course. But what I'd like to do is maybe if people like them, I might try and make a full set for anybody who's in year 12 and watching this, so that everything is ready for people going into next year 13 exams. But they take a long time to do, especially to do them properly. Okay, right. Determine the power rating of the hot plate. So we've got lots of information here. We've got the starting and the final temperature. We've got the mass of something, and we've got the time, and we've got the specific heat capacity. So to work this out, we can say that the energy supplied is equal to mc delta theta, but we want to know the power rating, and therefore the power is going to be equal to the energy transferred per unit time. So that's going to be the mass, which is 0.030 kilograms, times by the specific heat capacity, times by the change in temperature, which is going to be 35 minus 20, so that's 15, divided by the time it took to do this, which was 10 seconds. Probably I should have really written this out again, but the power is going to be equal to 82.35, which is 82 watts. So there we go, that first one there. Right. Okay, right, lots of good stuff in the chat. Okay, right. So that one there, that's fairly easy. I reckon this is very much a GCSE level question. You look at some data, get some numbers, and you work out an answer. Then it says milk chocolate melts at 45. Okay, this one here, so it says the student places a chocolate onto a hot plate and measures the temperature of the chocolate to be 35 degrees by placing a thermometer into its centre. But you can't really do that if it's a solid piece of chocolate, can you? Okay, we then have the chocolate melting and the latent heat of fusion. Calculate the total energy required to melt a 20 degree piece of chocolate. I guess we're going to assume that the mass is equal to 30 grams again. Okay, yeah, these questions are fairly straightforward. Are people talking about my biceps? It's a bit weird. Okay, right. Anyway, focus on the physics. So the total amount of energy. The total amount of energy is going to be equal to mc delta theta plus ml f. Okay, so that'd be my equation. So the energy is going to be equal to the mass, which is 0.030 times the specific heat capacity that we had last time. 1.83 times 10 to the 3 times the change in temperature. Well, if it's going from 20 to 45, that's going to be 25 plus LF, which is 4,000. Okay, now often in exams they don't tend to ask you the same skill again immediately afterwards. So the last question just wanted you to work out specific heat capacity, and we've basically used the same equation again in this one. So let's have a look at what this would be. 1.83 times 10 to the 3 times 25 plus 4,000 by 0.03. Is that right? Yeah, so I'd probably give that as 1.5 times 10 to the 3 joules to show that actually we've got an answer to two significant figures like the numbers we've got up here. Okay. Oh, cool, yeah. What's this? Yeah, I used to be in the military, but it seems a long time since I was out, like, having a bit of a fight in various places. That seems like a completely different lifetime ago. But yeah, yeah, the military is definitely great fun. Okay, right, right. Okay, are people having an AQA versus OCR battle? I would said that. So okay, I've taught OCR and I've taught AQA, and the thing is, if one of the exam boards was easier and more students got A stars in that exam board, all the schools would switch to the easy exam board. So it doesn't really matter if you are doing OCR or AQA, you'll have the same outcomes no matter which one you do. Now there might be some trickier papers in one exam board one year compared to another, but often if it's a trickier paper, they just then adjust the grade boundaries accordingly. So last year there was an easy or relatively straightforward AQA paper 3A, but one of the other papers was a bit more difficult. But OCR had a really difficult paper 1, but an easy paper 2. So it doesn't really matter yeah. I reckon it. Yeah, I reckon it doesn't really matter which one you do. Okay, yeah. So it doesn't matter. It's just physics. And if you actually look at the exam questions, the more exam questions you do, you realise that they're just physics questions, okay? And the people who do well are the people who are just good at physics. Okay, why was this not going to lead to a very accurate value? So they had a poor method. So for example, there are lots of things they did wrong. They didn't account for the energy loss to the surroundings. They maybe didn't measure the mass of chocolate accurately, because it doesn't say how they did that. And maybe if they had a larger mass, that might help things. Maybe they didn't exactly know the start and the end temperatures. Maybe as well. Yeah, there's loads of things wrong with this. So this one here is more of like a suggest why their method didn't lead to good value. So all you've got to do is, if it's a 2-mark question, I'd be thinking you want to have 2 separate bullet points. So maybe one was about the starting temperature that they assumed to be room temperature when it might not be that, and maybe another one about maybe they didn't account for the heat loss to the surroundings. Okay, right. The next bit here says, yeah, you try white chocolate. Number format and settings. How do I get my calculator to do amazing magical things? Basically, if you go on this one, it's shift setup, and then you go to input output, so that's 1, and then I think it's number 3, so you've got, it says line input, line output, so line I, line O. If you click on number 3, it then has like 2 lines for your stuff there. Beautiful stuff, right. And this is an OCR paper, but of course, if you are AQA kids, then a lot of the stuff that comes up maybe about specific heat capacity, you need for paper 2 in a couple of weeks' time. Okay, this question, I looked at it earlier, not so keen on it. We're going to assume that the legs are not attached to the top, or that the legs basically have no mass. And we're going to assume that all of the mass, so it says here basically the rectangular dining table of mass 28 kilograms and length 300 is supported by 2 rectangular pillars as shown. So basically all of the mass is in the tabletop. Okay, and if all of the mass is in the tabletop, we can assume that the centre of mass of that tabletop, oh, that's a bad diagram, isn't it? Look at that, that's like 120, but that's like halfway. Basically, this is going to be 28.0 G, so that's going to be the weight force acting down at the central point. Okay, define a moment of a force. Well, this is just GCSE. This is like too easy for an A-level question. The moment of a force is going to be equal to the force times the perpendicular distance from a line of action of that force about a pivot. Okay. Okay, right. So there we go. Definition, moment is just going to be equal to the force times the perpendicular distance from a pivot or to the line of action of that force, something like that. Okay, by applying the principle of moments, determine support force at pillar B. So I'd say you look at this and redraw it again. So here is the thing. That's the tabletop. At the central point, we've got a force down of 28.0 G. Okay, what we can do is look at the support force at pillar B. So there's going to be a force up at B, and there's also going to be a force up at A. Okay, now provided the legs don't have any mass and they don't contribute to this, otherwise if you had to include the mass of the legs in the mass of the table, then you wouldn't know where the centre of mass is. So the distance from here to the centre is going to be equal to 1.0 metres. And the distance from A to B is going to be equal to 300 minus 120 minus 50, which is going to be equal to, what's that, 170, is that 130? Oh. And so I think it's always good with moments questions to basically draw everything out like this. Oh, good. People are talking about they want to go in Apaches. Absolutely, yeah. Apaches, awesome stuff. Great stuff to work with, and the pilots are always really good as well. Right, so the moments. If we look at something like this where it's an equilibrium, we can say that the clockwise moment is equal to the anti-clockwise moment. The clockwise moment about point A is equal to the weight of the table, 28.0 times 9.81, times the distance from the pivot, which is 1.00 metres. And that's going to be equal to the anti-clockwise moment, which is caused by the force at B times the distance, which is 1.30 metres. So, anytime you get a moments question, draw your own diagram, look at how the clockwise and anti-clockwise moments are equal if it's an equilibrium, and then you can put some numbers in. So we've got 28 times 9.81 divided by 1.3, and FB is equal to 211.3. So I would say that's 211 newtons. Okay, is that right? So this one here, you should be giving the answer. I know, yeah, I think you should be giving this to 3 significant figures, because it's given you 3 significant figures up here, and here, and here, and here. Even though it's not labelled as 2, it's actually given as 3. So I think 3 significant figures is fine. Okay. Oh, Erin says, did I ever do the 6-marker question from the Paper 1 Masterclass? I haven't done it yet, actually. I do have it printed out, and I've carried it around with me. I took it to read before I went in the gym this morning, and then I read it this afternoon in Bath when I was doing some work, and then I read a bit this evening, but I haven't actually written it up yet. So what I will try and do is I will have a go at the 2024 6-marker question about gravitational fields for satellites and why you should launch something maybe from a plane rather than the equator. I haven't written it up yet, so apologies to Erin in the chat, but I will try and do that. Okay, that question, pretty straightforward. The boy decides to sit on the top of the table above pillar A. So there's a boy here. Okay, and then it says Describe how the support forces from both pillars change as the buoy moves from A to B. Basically, calculations are not required. Yeah, so basically, if you've got the force at A and the force at B, and there's a person moving from here, so that's the person, and they move over here, what we're going to find is that the size of the force at A is going to get smaller, and the force at B is going to be bigger. I think that's pretty much it, isn't it? Yeah, I'd say that's more of a GCSE question. Let's not go into that too much. The buoy has a mass of 46 kilograms. Determine whether the buoy can sit at the far end of the table to the right of pillar B without the table tipping. Support your answer with a calculation. So I think this is the question where yeah, I reckon. Okay, right. Somebody's saying that exercise can make you perform better on an exam day. Yeah, I reckon if you've got the choice between lying in bed awake at 6 in the morning thinking about your exam, scrolling through TikTok, or you're going out to do like a gentle workout or like a light jog or something, I reckon going out and doing a bit of exercise is going to be a lot better than just lying there not doing anything at all. Okay, right. Somebody says that did I make this? I didn't make this. I didn't do these, I'm afraid. I just took these from PMT. So these are some of the physics and maths tutor questions. What I did do, though, for anybody who wants to find more questions, I do have lots of practical style questions that are amazing, with like lovely tables, lovely pictures. And I did these for paper, the practical skills. So I've got them kind of available on my website, so you can actually download them and have a go at the questions and so on. But you can find these. Look at that picture there. Now that is a proper physics picture that I drew, isn't it? You can find these on my website. There's an OCR practical pack that you can download if you're an OCR person. Also, I do have some AQA paper 3As that you can buy on my website as well. Okay. Right, the buoy has a mass of 46 kilograms. Determine whether the buoy can sit at the far end of the table to the right of pillar B. So, what we're looking at here is if you've got the mass of the table, which is 28g, can the buoy sit here when they are 46g? And that distance from there to there is... Okay, so that distance is 1.30 metres. And this distance over here is going to be equal to 0.20 metres. Okay, now they can't. I think you don't even have to do a calculation to show that. The other thing is that if the table is tipping, then that means effectively that the other table leg over here isn't providing any force, so that's kind of going to be completely ignored from this calculation. Yeah. Right. Okay. So we'd say that, I guess, going anti-clockwise, we'd have say, yeah, basically you can see that the clockwise moment is bigger than the anti-clockwise moment, and therefore it will topple over. Yeah, I don't think that's a great question, really. Right, let's ignore that. The next one, they've got a question about something which is oscillating with SHM. So define simple harmonic motion. Basically, the defining equation for simple harmonic motion is the acceleration is going to be proportional to the displacement, but in the opposite direction. Okay. Where can you find the paper 3A questions? You can find them on my shop, which I'll show you. So basically, if you go to my website, if you click on, well, that's a new thing. Look at this. Okay, so that's something we've just put on today. It follows where the cursor is looking. So this is like the masterclass thing. So it's like, I think it's quite a nice thing. But look, you can see that the icon follows wherever the mouse goes. Anyway, enough of that. If you want to find these practice papers, go to practice papers on my website. You can get a free sample if you want there, so you can have a look at what they're like, and then you can basically buy them on my shop. So if you just head to the shop, you can find them for A-level physics. If you are an OCR person, as you are today, it's only £9.99, and you can basically get a whole set of practical skills. It's like basically 9 big exam questions, and you can basically have a look at that. And if you buy it today, because it's digital, you do get it by later this evening, or you get it in a couple of minutes really. So that's something that you might be interested in. And I guess as we're going through this thing, let's see if anybody's actually bought any in the last couple of minutes. It'd be nice if somebody did. Let's have a look. This is better than scrolling through TikTok, looking through your own online shop and seeing if people are buying things. Yes, people are buying stuff. We've had who's bought this? Yeah, definitely people are just buying this at the moment, which is amazing. That's pretty cool. Okay. Right. Oh, did somebody see that? Don't show the Shopify stats. Okay. Right. Right. Did anybody see any of my data there? Right. Yeah. So that's basically the definition of simple harmonic motion. The acceleration is proportional to displacement, and it's in the opposite direction. So that's basically 2 marks for kind of putting that out in words. Right. The next question then, we've got this. The simple harmonic motion can be described using the following relationship. The student takes measurements for the period of oscillation and then plots a graph of t squared against L cubed. How can they determine the Young modulus of the word? So, an answer like this again, you want to kind of draw a diagram to show if you've got t squared on the y-axis maybe against L cubed down here, how can that relate to this thing up here? So of course omega is going to be equal to 2 pi over t, and that means omega squared is going to be 4 pi squared over t squared, and that's equal in this case to exy cubed over 4ml cubed. Now I'd probably basically switch both sides around. There's probably a better mathematical term for that, so we'll kind of switch everything over. So we can say that t squared is equal to 4ml cubed, and then of course we're going to divide that by exy cubed, and then we're going to multiply this by 4 pi squared. Okay, so it's looking like there's lots of stuff going on. So I can then say that t squared is equal to 8m over exy cubed times L cubed. Okay, I think that's right, isn't it? Yeah. So, hello, says Manus. Says that they got an A 2 years ago. Oh my god, it's so good seeing so many people back in the chat who haven't been here for a while. I didn't cancel a 4s. Basically, oh, is that 4? Is that right? Oh, sorry. Is that 16, is it? Yeah, sorry, it's 4 times 4, so that should be 16. I was getting distracted by people in the chat who'd got A's a few years ago from using my videos, which is amazing. Okay, yeah, I guess it wasn't really reciprocal, is it? Am I correct? Basically, there's things I do, I forget the names of it, but if you know that there's that on the top and that on the bottom, you can just switch it around, so that's on the top and that's on the bottom. Okay, yeah, by the way, I'm too tired to do maths properly. Okay, so basically, we can then relate this to y is equal to mx plus c. Okay, and I think it's always worth putting like arrows to show what's what. So on the y-axis we've got t squared, on the x-axis we've got L cubed, and that means the gradient m is going to be equal to 16m over exy cubed. And therefore if we want to work out the Young modulus in this case, that would be equal to 16m divided by xy cubed multiplied by the gradient. Okay, so I guess that's what this question is about. It's looking at an unfamiliar equation and looking at how this could be used to work out a certain physical constant by plotting data. Okay, and then I guess that's basically the basis of the question that you then put in with a few more bullet points to kind of actually put it in a logical format. Okay. Okay. Right. Is that right? Pi squared. Have I forgotten the pi squared? Oh yeah, there's a pi squared, isn't there? Pi squared, pi squared, pi squared. This is why, if you want to watch some quality videos, rather than just watching me late at night at 10 o'clock going through physics problems, what you need to do is you basically just need to go to my website. I've got pre-recorded videos that are much better because all of my mistakes I edited out and I could have spent ages. Okay, right. Then we've got a graph here. Oh, here we go. What key points is important to master electricity? That's an amazing question. Let me just like that. So, to master electricity, you basically just need to know that V equals IR, and basically just keep applying the equation V equals IR, and also draw an electrical circuit out again, maybe multiple times, so you can add data to the question, so you know where the current is certain values, you know the resistance of certain resistors, and if you've got something maybe where there's a variable resistor or something changes, and you've got maybe a couple of different values of maybe the resistance in that circuit, I would say that draw that out several times, and that means that you then can make your working out a lot clearer. So draw out your own circuit diagrams, label everything, and then just work methodically through, often using just V equals IR to work out certain values. Okay, right. The same setup is submerged in water. On the same set of axes above, sketch the displacement time graph for the oscillations in water. So my first thing would be, if I'm going to look at something where there's some heavier damping, then what I'm going to do is just put in like a guideline, and it looks very much like a kind of exponential line on the graph like that. So I've got my guideline I've drawn in pencil, and then I'd probably be going over in pencil before I did it in pen, and therefore this kind of value would kind of do this, up to this point, up to this point. So what we'd have is we'd have a lower amplitude of oscillation, we'd have the same time period when we've got something where there's some damping, and we see something that looks a bit like this. That's a pretty lovely curve, isn't it? Not bad. Okay, yes, it's something which is kind of a lot heavier damped. It's hard to tell how much it would go up and down in water. It might even be more significant than that. Potentially it might be kind of something that kind of does this, but they just want to sort of see the rough kind of idea. So it might be something that looks like that potentially, if it's really, really heavy damping. So maybe that's the thing oscillating in treacle, and that's in water and that's in air. Okay, are there other predicted papers? These are not predicted papers. They don't know what's going to come up. These are just example questions that are similar in style to real A-level exam questions. Describe the difference between natural and forced oscillations. I'm not going to write this down, but basically if you've got a natural oscillation, something will oscillate at its natural frequency, but a forced oscillation is where you've got energy being put into the system each time, and this is often caused by this periodic external force. Okay, right. The damping on the metal plate is increased. Describe how this will affect the amplitude frequency graph. So if we had something where there's more damping, then we'd have a lower amplitude of oscillation, and the frequency at the peak would drop down to a lower value. So what you'd see is something that looks a bit like this. Okay, so this is now something where we've got something which has been damped, and as you look at the peak, it's gone down to a lower value, and it's at a lower frequency for this new damp value. Okay, is that all good? Nobody's cooked. You're going to be fine. You're going to be fine. Right. how many questions have we got left? So this is 21. Oh my gosh, it just goes on and on and on. Is this the last question? No, that's 23, 22. Do you want me to keep doing the rest of this? You can of course access this live stream later. All you need to do is go to my YouTube channel. If you haven't already done so, make sure that you do subscribe, and you can re-watch it whenever you want to. Right, people are saying, rest up, tomorrow. How do you work out theta in Young's slit? In Young's slit, theta is often not really mentioned. It tends to be in a diffraction grating where they give you a value of theta, and often you measure the value of theta because it's between the diffraction grating and the screen, and between maybe one maxima and the next maxima. And if you know that distance and that distance, you can use tan to work out theta if you're looking at diffraction grating. Okay, right. Somebody's saying, Nishi saying, can people please bring grade boundaries down on Friday, please? Well, it's a collective effort, people. Somebody says that AQA A-level physics sucked the life out of them. Jack, shh, be quiet. It's fine. It was absolutely fine. And Jack, you're doing well now, despite whatever happened last year. Okay. Yeah, right. AQA is painful. Is cramming the night before the exam worth it? No. By this point, the night before your exam, the very, very last evening, do a bit of revision. Make sure you're confident with every bit and piece, with all the sort of bits and pieces. In the next case, just to get some rest and so on. Okay. Right. Right. Okay. Right. Should we do? I might just push on, to be honest. And if you don't watch it now, that's fine. Head off. And it's been obviously amazing to have you here tonight. But I reckon I could probably do this in about half an hour. So what time is it? It's about 10 o'clock at the moment. Let me just check what's going on. Okay. It's also actually interesting to see if anybody's actually watching me, or what my live stream looks like myself. So if I go to my channel, it's me. Okay. That's so weird seeing myself there. Okay, right, let's lock in. So, explain what is meant by the term redshift. Well, redshift is, when you've got a star or a galaxy or some object like that, and the light that it emits is shifted towards the red end of the spectrum because it has a relative recessional velocity to the Earth. So that's, I guess, what we mean by redshift. Oh, let me just get my piece of paper. Okay, so I'm not going to write it down, but you know what this is. If you haven't already done so, get yourself some flashcards. Light from a distant galaxy is redshifted by this much. The measured wavelength is this. So I think this is probably one of the hardest questions I saw in the paper. Within the OCR thing, it does say that the change in lambda over lambda is equal to the change in frequency over the frequency, which equals V over C. So I think that's probably one of the equations we're going to be using. Well, it definitely is anyway. So, determine the wavelength of the given line in the spectrum when measured using a light source on Earth. So what we're saying here is that light from a distant galaxy is redshifted by this much. So this is difficult because they've given us the redshift in. So they've given us basically delta F and the measured wavelength of light from this galaxy, and they've given us lambda over there. Okay, and determine the wavelength of the given line of the spectrum when measured using a light source on Earth. So my approach would probably be to say, what's the best way to do this? This isn't a nice question, is it? Thing is, space and cosmology is amazing. I think that this OCR question isn't phrased very nice. Yeah, you only get given delta F, so you get given delta F, you get given lambda. So okay, let's say that this is the measured wavelength from the galaxy is this, and then you've got the wavelength from a light source on Earth is lambda. So I'm going to say that's lambda 2. Okay, so let's say basically lambda 1 is the stretched one, and lambda 2 is going to be the actual value of the wavelength. So that'd be my kind of first approach. So we know, of course, that we've got the wave speed equation that v is equal to f lambda. So that means the frequency is equal to v over lambda. And so, or sorry, the speed of light, c equals f lambda, so the frequency is equal to c over lambda. And that means then that the change in frequency is going to be c over lambda 1 minus c over lambda 2. So we've got the difference in the first frequency and the difference to the second one is this much. And therefore, we want to find this, don't we? So lambda 2, so c over lambda, sorry, this is like me thinking really slowly, okay? This is not a nice one, okay. Just divide speed of light by frequency. Okay, so I'm going to say c over lambda 2 is equal to c over lambda 1 minus delta f, and therefore delta 2 is going to be equal to c over lambda 1 minus delta f. Is that right? I think that's what it is. Let me just work it out. So, sorry about this. I'm going to just go on to another bit of paper. And then convert that back into the wavelength. So divided by okay. Excuse the kind of the silences. So is that right? Have I? So that's given me a wavelength which was longer than it's before. So I must have messed up somewhere where that should be positive. And if I do that, yeah. Okay. Oh, it's hot. Add, yes, add, change. Okay, right. Yeah, okay, so, right, 3 times 10 to the 8 divided by 5.61 times 10 to the minus 7. Add that change, sorry, is 2 plus 2.1 times 10 to the 13. And then 3 times 10 to the 8 divided by answer is 5.4 times 10 to the minus 7 meters. Okay, thank God. Basically, that is the answer. Yeah, so we know that that was the increased wavelength, so it must be less than that, so it must be 5.4. Sorry about that. Okay, maybe what I need to do is kind of chop up bits of this live stream and just make it look like it's all gone perfectly well. Calculate the speed of the galaxy relative to the Earth. So we know, or we can work out the frequency, we can work out the change in frequency, and I guess we can use this equation over here, where we can say that V over C is equal to delta F over F. Is that right? So if we want to find V, this is just going to be equal to the speed of light, 3.00 times 10 to the 8, times by our change in frequency, which was 2.1 times 10 to the 13. We're going to divide that by, I guess, our original value for the wavelength, which we need to work out the frequency. And of course, the frequency is going to be equal to c over lambda. So that's going to be 3.00 times 10 to the 8 divided by this new frequency of 5.40 times 10 to the minus 7. So that's going to be our change in frequency over the original frequency, and we can work out the original frequency from the original wavelength. Am I back on track? Okay. Okay, so we've got 3 times 10 to the 8 divided by 5.4 times 10 to the minus 7, 2.1 times 10 to the 13 divided by answer by 3 times 10 to the 8 is 1.13 times 10 to the 7 meters per second. That all look all good? Yeah. Okay. Right. What are people saying? Can I have free flashcards besides particles cards after donating £4? Right. I'm afraid I don't have any other flashcards apart from the particle ones. Do people like flashcards? Do you think that I should be spending like weeks and weeks making the most awesome set of A-level physics flashcards? And if I made them, obviously probably not for all of you guys ready for your exam later this week, but do you reckon the year 12s who are coming through might find them useful? Yes. Okay. Yeah. Okay. What my favourite plane is? I think... Oh, it's a good question. What's my favourite plane? Definitely like an A10. An A10 is pretty awesome when you hear the guns going off in real life. But I never called in a gun strike with an A10, so that's one thing I never kind of ticked off my list. But Harriers are pretty good, or the AV8s that the US Marines had, they've been pretty cool. Yeah, so a lot of good stuff there. Right. Did I say a bad word? Okay. Estimate the distance in meters between the galaxy and the Earth. Use Hubble's constant. So this, I guess, goes back to the equation. This goes back to the equation that we're given that says V is equal to H naught D, and we want to find the distance. So the distance is going to be this recessional velocity divided by Hubble's constant. Now the recessional velocity we worked out last time as 1.34 or whatever it is times 10. Or whatever it is, 10 to the 6. So that's going to be the distance in meters. Sorry, that's like not the best way to display it. We're going to divide that by Hubble's constant. Now it says, and this is a skill all of you need to develop, we need to convert this from kilometre per second per megaparsec into meters per second. So this is going to be 65,000 meters per second per megaparsec. And then what we need to do is we need to divide that by a megaparsec. Now, megaparsecs, they're given to you. We know that a parsec is 3.1 times 10 to the 16. So we just need to multiply that by 10 to the 3. Okay? So, what we then do is... is that right? Hold on, that's not right, is it? So, is my brain sleeping? Okay. Right. This gives me an answer equal to 5.4 to two significant figures times 10 to the 21 meters. So 5.4 times 10 to the 21. Okay. How do you increase the size of the font in your calculator? I'm not sure, to be honest. Yeah. Yeah, so basically I've got 10 to the 16 is my that's my parsec. Oh no, is it a mega? per megaparsec. So times, what have I done there? What have I made a mistake? It's times to the power 6, it's not 365,000. Oh yeah, sorry, that should be times 10 to the 6, that's 10 to the 4, that's 10 to the 4. Sorry, mega is power 6. Okay, it is. This is why, people, you shouldn't be working at night like I am now. You should be getting to bed, and you definitely shouldn't be doing an all-nighter the night before your exam. Okay, right, so we now have the black body radiation curve for 3 different stars, P, Q and R. Which of these is the hottest? Well, first of all, if you've got something like this and you've got to guess which is the hottest, it's either going to be the biggest or the smallest, never the one in the middle. But the one which is hottest is going to be P, so that's 1 mark for stating that. And the reason being that it's got the maximum wavelength at the smallest. It's got the maximum intensity at the smallest wavelength, and therefore it's going to be giving out light with the highest range of wavelengths and the most energy, because it's got the biggest area under that line as well. Okay, so that first one shouldn't be too bad. So its peak wavelength is inversely proportional to the temperature. Peak wavelength is the smallest, so it's going to be the hottest. Calculate the surface temperature of that hottest star. So not a good question, because I already asked this earlier. So basically this is this first one is like a repeat of what they had in the multiple choice things. So to work out the value there, I reckon that the peak wavelength is going to be about 250. So lambda is going to be about 250 times 10 to the minus 9 meters. And that means the temperature is going to be equal to Wien's constant, so 2.9 times 10 to the minus 3 meter Kelvin divided by 250 times 10 to the minus 9, which I guess is about 11,600, so I'm going to say about 12,000 Kelvin. So I think that something like this, 2 significant figures, is absolutely fine when you look at the kind of scale on the graph there. Okay, right. Okay, so this graph, there's lots of stuff here about the Big Bang and the older discredited steady state theory. Use the graph to conclude which theory of the universe has been deemed correct. I don't know if this is a great question, but basically I guess what we can do from this is we can look at the temperature that corresponds to this particular value. So again, it's the same skill it's testing, but maybe if the wavelength is about 1.1 times 10 to the minus 3 meters, we know that the wavelength is in the microwave part of the spectrum, so it's not visible or anything like that. So we basically have these microwaves, which I guess we can detect as part of the cosmic microwave background radiation. And of course, I guess we could look at the temperature, so that's 2.9 times 10 to the minus 3 divided by 1.1 times 10 to the minus 3, which is about 2.6 Kelvin, which is kind of the temperature that we see in space as well. Yeah. Do you talk about CMBR? So I think, yeah, stuff like this, you'd have to talk about the fact that there was cosmic microwave background radiation, which gives us one piece of evidence for the fact that there was this Big Bang and how that energy, the kind of really high energy photons, have stretched out as space has expanded. And I guess you could also then link this back to other things about the Big Bang theory. So yeah, a big old question, but I reckon don't worry about it too much. The last question, where would the passenger feel the most squished in their seat? So they'd feel the most squished in their seat at point C, because at point C you've got the centripetal force being provided by the reaction force upwards. So if you're in the seat, the force that you feel squashing you in is actually a reaction force pushing you up, and therefore C is going to be the point where you'd have the largest normal contact force on you, and so you'd feel squished up here. Whereas when you get to B, the normal contact force can reduce to 0, because then it's your component of weight which is actually providing the centripetal force towards the centre of that circle. Okay, somebody says that they could pull 9 Gs for at least 30 seconds. I don't reckon you could. Although it is interesting, when you do go, if you ever get a charter jet or something like that, when you're in a sustained G turn, it is crazy how as the blood leaves your head, you do see this kind of like cone of sort of, your vision kind of goes quite small if you're in a fighter jet. Okay, right. On figure 23.1, add labelled arrows to show the forces acting on the cart and passengers at position B along with their direction. So it's not a very big diagram. So you'd have the force. I'm going to do this just to make it a bit clearer. You'd basically have the weight, force equation for the cart at position B, and link it to the centripetal force. So the centripetal force, Fc, is going to be equal to the weight force plus the normal contact force. Okay, now there's not always particular symbols for these different sorts of forces, so just make sure it's really clear what those are. Okay, so I've linked the centripetal force to the weight and the normal contact force. Is this lagging at the moment, is it? Let me just see what the CPU usage is. All good, should be all right. Am I dropping frames? Is this all good? Have I been caving? I have, but it's a bit of a weird hobby, but I've only done like little bits and pieces, nothing serious. Okay, right, so that's all good. Then we go to 20, the next bit. Show that the minimum speed required for the cart to continue its circular motion at the B can be given by this. So I would say for this one, the centripetal force is equal to mv squared over r by the weight of that cart, which is going to be equal to mg. Okay, so that would be my equation. And therefore, these cancel. So v squared over r is equal to g. So v is equal to the square root of gr. Okay, so this is the case where at the very top of that track, cart's going over, the only force acting on it at the minimum speed is their weight acting down, mg, and this weight force is going to be providing the centripetal force, which is mv squared over r. And this is where people feel weightless, because there's suddenly no longer... Is it somebody says it's a free Wi-Fi in McDonald's. I should be... Let me just have a look at the settings. So, 1 second. I should be... It does say... Okay, press the on and off button. Now it's good. I think it's just so late at night. Right. I think somebody says, can you reference centrifugal force? No, if you put in the word centrifugal, they will automatically take off a whole grade off your final grade. So never use the word centrifugal, only ever use the word centripetal. Okay, it then says the cart enters a circle at point C with an initial speed u, and it gives the cart the minimum speed needed at B. Use conservation of energy principles, show that therefore u is equal to 5 root 5 gr. So, I guess the kinetic energy at C is going to be transferred to the kinetic energy at B plus the gravitational potential energy EP at B. So, in order to go over the top, then its kinetic energy must be equal to a half times m times v squared. but last time we said that v is equal to root gr, so that's going to be our minimum speed to go over the top. So half mv squared is going to be half mgr. The gravitational potential energy at the top of that circle is going to be equal to mgh, but I guess the height it's gone through is going to be equal to 2r, so that's going to be 2r, and the initial kinetic energy is going to be a half mu squared. Okay, so that'd be my approach. So the initial kinetic energy ends up as the final kinetic energy of that moving cart as it goes over the top, plus its gravitational potential energy, and therefore the m's cancel. And so we can say that if I multiply everything by 2, u squared is equal to gr plus 4gr, because you've got 2r times 2, so that's 4gr. So u squared is equal to 5gr, so u is equal to root 5gr. Cool, I'm glad I did that. Yeah. Given that the radius of the circle is about 10 metres, determine the minimum height the drop needs to be to allow the cart to complete the loop. So I think this one is actually just a simple, easier question than this. Basically, the initial gravitational potential energy, mgh, is going to be equal to a half mu squared. So that's going to be a half m5gr. Is that right? And so h, because they're going to cancel, h is equal to 5gr over 2g. So I think the g's cancel. So h is equal to 5r over 2. So if r is 10, that's going to be 50 over 2, which is 25. Tom Rock's maths will be proud with that kind of mental maths. Okay. Yeah, so people are talking about multiple choice stuff. Yeah, sometimes there are definitely multiple choice questions that you can do in 20 seconds. Other ones, you look at them and go, I cannot do this. And you just got to leave it and move on and kind of come back at the very end of the exam. So sometimes you get multiple choice questions which are easy, and sometimes they're really difficult. Right, explain the modifications that we make to this roller coaster in real life to ensure safety and the reasons for these changes. Well, I think there'd probably be a lot of changes, but it's hard to tell. The biggest one, though, is if somebody's moving along the flat at the bottom and then they suddenly go into a circular path, they basically go from zero acceleration to a high centripetal acceleration. And the rate of change of acceleration is called the jerk, and that's why real roller coasters aren't actually circular. If you look at a real roller coaster, they have a gradually decreasing radius, and then the top bit is the spiral, and then as it comes down you have a larger and larger radius. So if you were to look at this point over here, the radius would be really big. If you look at this point, the radius is a bit smaller, and if you look at this point, the radius of curvature is even smaller. So real roller coasters don't actually have it doesn't go flat to a circle like you might have seen people making to kind of go on their bikes and BMXs and stuff. But basically a real roller coaster actually has a decreasing radius up until we get to the top point. Okay, I reckon we're done. I'm done anyway. So I reckon those questions were a good source of questions. A lot of them were relatively straightforward. And I definitely think that when you go into your exam on Friday, the real questions are going to be probably a little bit more challenging, but also clearly structured, and they really kind of get quite progressive throughout the question. So yeah, I have made it. It's been great to have so many people in the chat. Chidambaran, for example, I see that you've been here quite a lot. AG2, San, excellent stuff. Yeah, loads of people here. Let's see the floor. Well, the floor is basically a floor covered in bits of paper. So all it is the bits of paper go off to one side. And basically what I'll do is I will be cleaning these up tomorrow morning. I'm also actually filming with the Ogden Trust. So the Ogden Trust, if anybody's heard of them, they do lots and lots of physics support for people. They're coming to my office tomorrow. We're going to film some videos. I probably won't be doing I won't be doing any big A-level live streams tomorrow night. I might do a GCSE one potentially. But of course, if any of the rest of you are going to be here on the other nights, if you go to alevelphysicsonline.com, you can find that I've got masterclasses for OCR and AQA over the next couple of days. So if you want to do some last minute OCR revision as well, you can find me and a small group of people, because there's not going to be that many, and we'll be doing a masterclass this Wednesday from 5 till 7. So you can finish school, come back, have a snack, or eat your snacks while watching me, and then by 7 o'clock you've got the evening to kind of do what you need to. So yeah, if you want to, you can find all of my masterclasses on my website, and I shall see you all soon. Goodbye.